in this chapter. It's going to be the main thing that we look at in this chapter. The other thing that we're going to look at is solubility equilibria. So this is called kind of just KSP for short. We'll get to this at the end, and I'm not as interested in it. But buffers is the main thing that we're going to talk about in this chapter. Okay, so also just as a note with respect to the homework that is open, this acid-base homework, it also has a bunch of buffer questions in it, okay? And so because of that, this homework that is open, that's called acid-base homework, whatever, is going to be worth 55 points total, okay? And there's going to be a second homework that's not going to have as many questions, that's going to deal exclusively with KSP. This is going to be worth 15 points total. So just note that this guy is large, lots of problems, and lots of stuff that we haven't yet talked about, but it's going to be worth a lot of points because of that, okay? So moving forward, just make sure to note, finish your acid-base homework once we get done with all the problems that you can actually answer. Okay, so let's start talking about buffers because they are great. All right, so we're going to start talking about this in terms of a cautionary tale, the danger of antifreeze. Okay, so we don't have to deal with too much antifreeze in our own garages, etc. here in Arizona because we don't really have any cars that freeze in the wintertime, right? But what's wrong with antifreeze, right? So a lot of animals will tend to be attracted to drink antifreeze. What would happen to them long term if they were to do that? Right, so they're going to die, right? So that's an issue. Pets and wildlife, when they drink too much antifreeze, eventually will perish, okay? So why is that? So this comes back to the fact that antifreeze consists of this molecule which is called ethylene glycol, okay? So ethylene glycol looks something like this. It's an alcohol, and more specifically, it's a diol. Okay, you don't have to know the structure of antifreeze, but this is what it looks like. Number one, why does it actually attract animals to drink it? It's sweet. Okay, so that's why they're attracted to it. If you would actually drink it yourself, it would taste very sweet. Number two, the initial effects of drinking or consuming antifreeze is essentially drunkenness. So if you were to consume antifreeze before you died, you would feel very drunk. It's just like an alcohol, okay? All right, so what is the actual problem with respect to ethylene glycol? What is it actually toxic to our systems? So when we take ethylene glycol by itself, it is harmless, right? But what happens is this guy gets shuttled to the liver, and in the liver, it is metabolized to something called glycolic acid. So this glycolic acid is a carboxylic acid. We have talked about carboxylic acids being fairly acidic, okay? So it's this carboxylic acid that causes the problems with respect to ethylene glycol. All right, so this guy is acidic, especially compared to the alcohol that it was derived from. So this glycolic acid is going to enter your bloodstream, and it's going to act like an acid, right? So what's that going to do to the pH of your blood? It's going to increase the proton concentration, which is going to lower the pH, okay? So this is where the problems come in. Number one, the pH of our blood is very highly regulated, okay? So we keep it at about a pH of 7.4, okay? Lots of bad things can happen besides what I'm going to talk about now if our blood pH actually swings between any type of region outside that pH of 7.4. How do we do this, though? How does our body essentially keep our blood pH within this very tightly regulated range? It uses buffers, right? So we have lots of buffering systems in our body with which we can maintain our blood pH. One of the most important ones that we're going to talk about is this carbonic acid bicarbonate buffering system. So this is present in our blood, okay? So carbonic acid is a nice little weak acid, and again, the purpose of buffers is to maintain our pH at a regular normal point. So if we add any type of strong acid, add any type of strong base, they're going to react with it, and again, maintain our normal pH, okay? So carbonic acid, if we add any type of strong base, is going to react with it, it's going to form water, as well as its conjugate base, the bicarbonate ion. Bicarbonate, which is the other component of this buffering system, if there is any type of strong acid added, is going to react with the strong acid and form more of its weak acid, carbonic acid. Okay, so this is a very important buffering system in our blood. Okay, so that's great. We have our blood buffers. They keep our buffer within a nice tight pH range. All right, so what happens when we consume too much of this ethylene glycol? It's metabolized to this acid, glycolic acid, and it enters our bloodstream. Okay, so if there's too much of it present in our bloodstream, it's essentially going to overcome our body's ability or our blood's ability to buffer. It's essentially going to overcome the amount of bicarbonate that is present in our blood. At that point in time, we essentially collapse our buffering system, and now we just have acid spewing forth into our blood. Okay, so what again is going to be the problem with that? So there's lots of different things, but the one that we're going to focus on is the relationship between protons or acid as well as hemoglobin, the molecule that carries oxygen, right? So everyone knows what hemoglobin is? So hemoglobin picks up oxygen in the lungs and transfers it out to the tissues, okay? It has an intimate relationship with protons. And its ability to pick up oxygen and then also release oxygen also has an intimate relationship with protons, right? So if we have our hemoglobin and it's in the presence of excess protons, so very low pH, what is that going to do to the equilibrium of this reaction? So if we have a bunch of this guy, it's going to shift this reaction to the left, right? And so what's that going to do to the ability of hemoglobin to pick up oxygen? Because this is hemoglobin with oxygen bound. So if we shift this reaction to the left, hemoglobin is not going to be able to pick up oxygen any longer. Okay? What's the problem with that? If hemoglobin can't pick up oxygen in our lungs, what are we going to do long term? We're going to suffocate, right? And actually, that's what you see animals do on these, like, their last throes of dying because of drinking this antifreeze. They appear to be suffocating. They're essentially breathing in very rapid, shallow breaths. Even though oxygen's entering their lungs, hemoglobin can't pick it up and diffuse it to the tissues, and so that's why long-term they die, okay? Okay, so again, thank goodness for our blood buffers because they protect us from these various causes and consequences. Okay, so one more thing. There's a nice little treatment that if you know something or some animal that has consumed too much ethylene glycol that you can do to try to prevent it from dying. Okay? And that treatment is to flood its system with ethyl alcohol. So what is ethyl alcohol? It's a fancy word for what? Just alcohol, right? So ethanol. So this is just ethanol, which you would consume on the weekend, drinking your vodka or your tequila or your beer. Okay? Beer. That's great. That sounds really educated. Okay, so one treatment to prevent the animal from perishing is to essentially get it really drunk as quickly as possible. So what's that going to do? So the enzyme that metabolizes that ethylene glycol to the carboxylic acid, glycolic acid, also metabolizes ethanol to its long-term waste product. Okay? That enzyme has a much higher affinity for ethanol. So if you flood the system with ethanol, that enzyme is going to preferentially pick up the ethanol and metabolize it. The ethylene glycol, because it's not being picked up, is just going to essentially flush through, and we're going to excrete it as waste. Okay, so worst case scenario, if you ever figure out that you have drank antifreeze, you should then go forward and get very drunk, and hopefully you will not die. Okay, so that is a nice cautionary tale of what buffers do and how important they are to our system. All right, so now let's actually specifically define what a buffer does, okay? So a buffer, like we said, is going to be a solution or a system that resists wild changes in pH upon addition of strong acid and strong base. And so I tried to preface this as wild or drastic changes in pH, okay? They're going to do that. Buffers are going to work by neutralizing whatever added acid and base we have provided them, okay? Now, how do we make a buffer? A buffer has to contain the following. It has to contain significant amounts of a weak acid as well as significant amounts of its conjugate base. Or if we have a basic buffer, it has to have significant amounts of a weak base, as well as significant amounts of its conjugate acid, okay? So a nice example of a buffer is given here. So in this buffer, we have a weak acid. This is acetic acid. To be a buffer, it also has to have significant amounts of its conjugate base, right? And so what is the conjugate base of acetic acid? Acetate, right? So to be a buffer, we have to have a bunch of this guy. We also have to have a bunch of this guy. If it's one and not the other, then you don't have a buffer, okay? Okay, so how are buffers actually going to work? So let's take this acetic acid acetate buffer and look what happens when we add something like a strong base, something like sodium hydroxide. So if we add a strong base, we have this buffering system, again, acetic acid, sodium acetate, or some sort of acetate, and we add a strong base. So a strong base would be the addition of hydroxide ion. Which one of these forms would hydroxide react with? The weak acid or the conjugate base? So we have our little OH minus, so we've added our strong base. Is this going to react with the acid, the weak acid, or the conjugate base? What do bases react with? Acids, right? So if we add strong base, then this guy is going to react with the weak acid. And what is it going to form? An acid and a base. What is the number one thing that they form? Water, right? So we've got OH plus an H gives us H2O. And then what's left behind from the acetic acid if we've taken an H from it? Just acetate, right? So if we have a buffer and we add strong base, the weak acid is going to react with it. It's going to produce water, and it's going to produce its conjugate base, right? So this guy is not a strong base. It's a very, very, very weak base. So again, neutralizing the strong base produces acetate. No big deal. It's not going to change the pH that much, okay? All right, so now what if we added strong acid? So if we add strong acid, we'll go back to our nice little acetic acid acetate buffer. So we would add strong acid. This would be present as like an H plus ion, let's say. So we have our H plus ion that we have added, our strong acid. Who is H plus going to react with? The weak acid, acetic acid, or the conjugate base acetate? Conjugate base, right? So it's going to react with our conjugate base. The conjugate base is going to neutralize that strong acid added, and who is it going to form? Just more acetic acid, right? Which is a nice weak acid. Okay, so this is how buffers work. Strong acid, strong base is added. They react with it, they neutralize it, and they produce either more weak acid or more weak conjugate base. Okay? Okay, so let's take a question, try to make sure that we've got that. So I'm looking at the definition of what a buffer is. So I want you to tell me, between these four solutions, which of these would act as a buffer? Okay, so if you haven't got your answer in, most people have. Unfortunately, only 35% of you, 38% of you got this correct. So that's not great, I would think. So again, what does a buffer have to contain? We have to have significant amounts of a weak acid as well as its conjugate base, right? So a lot of people liked this one. What is the problem with B though? What type of solutions are those? So these guys are strong bases, right, or strong acids. So HNO3 is a strong acid. You cannot make a buffer with a strong acid. It is an impossibility, okay? If we go down here though, HNO2, nitrous acid, this is a weak acid, right? And then its conjugate base is going to come in the form of this pretty little soluble salt, right? So NO2 is the conjugate base of our weak acid. That's how we're going to get these conjugate bases into solution, being the anions in these soluble salts. The answer is B. So B, weak acid, conjugate base. Need a bunch of it, okay? Okay, so now let's talk about pH, right? Because that's all we do. Let's talk about pH and how all of these various things affect pH. How you're going to calculate the pH, whatever we want to calculate, okay? Okay, so buffers utilize something that's called the common ion effect, okay? So let's imagine that we have just a solution of acetic acid, so a nice little weak acid, right? And we want to know what the pH of that solution is, right? So we could do that, we could calculate that, we can make an acetic acid solution in the lab, we could go measure it with a pH meter, okay? So let's say we do that and we find the pH to be about 2.9, all right? So now, what effect on this equilibrium of this weak acid are we going to see if we add in something like sodium acetate? Right, so again, sodium acetate is a nice soluble salt. This is how we're going to get these conjugate bases in here. This is going to introduce the conjugate base of this weak acid, a common ion in this overall reaction, right? So if we introduce this guy, what's that going to do to this equilibrium? Is it going to shift it to the left or the right? Back to the left, right? So introducing a common ion like sodium acetate or acetate is going to shift this reaction to the left. What's going to happen to the pH? What's going to happen to the H3O plus concentration because of this? Comparatively. We shift to the left, this guy is going to decrease. What is that going to do overall to the pH of the solution? It's going to increase it, right? So if we do that, and we compare the pH of a solution that has weak acid, as well as a significant amount of its conjugate base, we're going to see an increase in the overall pH, okay? And again, it's because they have a common ion, and that common ion affects the position of equilibrium. Okay, so now what if we wanted to actually calculate this instead of measuring it in a lab? How would we go about doing that? How have we calculated weak acids thus far? pH of weak acid solutions. Done an ice table, right? Ice table. So on and so forth, forever. Minus log of H3O plus, right? But how do we get H3O plus? Ice table, okay? So let's look at that. Let's say we want to calculate the pH of a buffer, right? We have a buffer that contains 0.1 molar of acetic acid and 0.1 molar of sodium acetate, which is, again, the way we're going to get a beautiful little conjugate base into solution, okay? So where would we start this? We'd start by drawing our I, our C, and our E, and we would go about going ahead and filling in what we know, right? So for this guy, what is our initial concentration of weak acid? 0.1, so we can go ahead and fill this guy in. Right? We can leave this one alone. Now what changes? This is kind of like the polyprotic acid situation, right? So now H3O plus we can still assume is 0, but we have a significant amount initially of our conjugate base, right? So what's going to go in for acetate? 0.1 as well, right? So 0.10 is going to be our initial concentration of acetate. Because again, this salt breaks up into sodium as well as acetate. We have 0.1 of that salt, so we're going to have 0.1 of acetate. Okay, so now how do you think we're going to represent our change? This unknown variable x, just like we have before. And so at equilibrium, all we're going to do is sum the columns, and sum the columns. Now what do you think is going to happen? Solving for x. We want to get x because that's our H3O+. We're going to plug it in to our acid ionization equation, right? So we've looked up acetic acid. Its Ka is 1.8 times 10 to the minus 5. So now we'll plug in the concentration of our products, x, 0.100 plus x, all over the concentration of our reactants, 0.100 minus x, and then we'll solve. All right, so do you think we want to solve this as is? Looks super ugly. No one wants to deal with that. So what are we going to do instead? We're going to ignore our little x on bottom, because again, it's going to be super small. What else are we going to ignore? Right, so the plus x on top. So if this is so small that it's not going to do anything subtracting it from 0.1, then it's not going to do anything to adding it to 0.1. Okay, so when we do that, we end up with 1.8 times 10 to the minus 5 is equal to x times 0.10 over 0.10. What happens to the 0.1s? Cancel. This guy goes away, this guy goes away. We are left with x equal to 1.8 times 10 to the minus 5. Is that it? So this is x now, but we want the pH of this buffer solution. X is H3O+, but if I want the pH, I'm going to need to take the minus log of this guy. And so when I do that, I get a minus log of 1.8 times 10 to the minus 5, that's 4.74. Expected to get a lot farther than that. It's my talking at the beginning. Might as well, let's do this problem and then we'll be done. So I have a buffer. This is formic acid, a formic acid sodium formate buffer. The Ka for formic acid is 1.8 times 10 to the minus 4. And all I want you to do is calculate the pH of this buffer. Okay, so I think that whoever's going to enter an answer has probably already entered one. So we got a 60% correct rate here. I think people are tempted to just think that the proton concentration was going to be equal to the Ka, which is true as long as the concentration of our weak acid and conjugate base are equal to one another. But in this situation, they are not, right? So we have a concentration of 0.25 molar of our weak acid. And then what's the concentration of the conjugate base, which is formate here? 0.5, right? So this guy's 0.5 initially. We'll assume 0 minus x plus x plus x. Try not to read off everything I'm doing. Plus x. So these guys, now they're ready to go into our little equilibrium constant expression. All over 0.250 minus x. Again, we're going to assume that we can ignore x. So that's going to lead to 0.5 x over 0.250. Right? So now multiply by 0.25, divide by 0.5. We get x equal to 9 times 10 to the 5th minus 5. And so then the minus log of that is 4.05. Okay. So unfortunately, so I do this, I'm like, hey, this is where it all comes from. It goes back to weak acid equilibria. But in reality, there's also a nice handy equation that makes this so much easier to do. Okay? So the Henderson-Hasselbalch equation is how you guys are going to calculate the pH of a buffer moving forward. I'm not going to talk about that today, though. We're going to wait until next time. But ice table, all of that, it all boils down to this beautiful little equation. It's much easier to utilize. Do a problem to illustrate this. Okay, I have a buffer, right? I have a weak acid here. This is hydrocyanic acid? No, cyanic acid. Oh, man. I shouldn't take the stoichiometric. No, what is it? Nomenclature. I hope I don't have to take that because that's not good. So we have cyanic acid, right? We have a specific concentration. And then we also have this salt, potassium cyanate, okay? I give you the Ka for HCN, the cyanic acid, and utilizing the Henderson-Hasselbalch equation, I want you to determine the pH of this solution, of this buffer solution. So I'm going to go ahead and write out my Henderson-Hasselbalch equation. pH is equal to pKa plus log. For this problem, I have a weak acid. This is HCN. Who is the conjugate base of HCN? Right, so the conjugate base of this guy is Cn minus. Okay, so this is going to be log of the concentration of Cn minus over the concentration of weak acid, which is HCN. Okay? All right, so now to calculate the pH, I need a couple of things. I need the pKa. I have the Ka, so how do I determine the pKa from the Ka? So reminder, so P of anything is minus log of that thing, and so pKa is just going to be minus log of Ka. So to determine this, I'm just going to take the minus log of my 4.9 times 10 to the minus 10th, and I get a pKa value equal to 9.31. Okay, so that's number one. We have to get the pKa. So I'll go ahead and plug that guy in. Now, concentration of Cn, my conjugate base, right? I have provided into my solution this salt, this potassium cyanide. It had a concentration of 1.7 molar. How much Cn is this salt going to provide me? How much conjugate base is it going to give me? If we assume that this is completely soluble. So this guy, our little salt, is going to break up into little potassium ions. as well as cyanide ions. So for every 1 KCN, how many CNs do I get? 1, right? So this is giving me the exact same concentration of my conjugate base, okay? So that's how I'm going to get my conjugate base concentration, 0.170. What is my concentration of weak acid? That's fairly easy, right? They tell us the weak acid concentration. I don't even have to think about that. That is this 0.25 molar, right? So I plug that in, 0.250 molar. I will take the ratio of the 0.17 divided by 0.25 and take the logarithm of that. So 9.31, that ends up being a minus 0.167. And then at the end, there's no x's, there's no anything like that. All we have to do is add these two things together. And so the pH of this solution is 9.13. Okay, so this way, comparatively to doing the equilibrium problem, which involves an ice table, finding x, right, taking the pH from the x, etc., which one do you think is easier? Which one do you like more? This one seems to be fairly easy, right? So when would you use one versus the other? It's not a trick question. Oh, well, I guess maybe could be. It's not really a trick question at all, right? One of the big assumptions that we make in our ice tables and in our equilibrium problems is we always ignore x. That's a big assumption that we also make in the Henderson-Hasselbalch equation. We are ignoring the x or the contribution of x, okay? So, has there been any point in time with respect to acid-base chemistry where I have not allowed you to ignore x? No, okay? So, because of that, equilibrium versus Henderson-Hasselbalch, it would be my suggestion that you always use Henderson-Hasselbalch in determining the pH of a buffer, because I think it's a lot easier than having to draw out an ice table, etc. The only time that you would not be able to utilize Henderson-Hasselbalch, and you would have to go in and actually solve the equilibrium problem using ice tables, etc., would be when you could not ignore x. But again, I've never had to do that before, right? So, for the most part, you should always use Henderson-Hasselbalch because it's easier and it's prettier for the most part, okay? Okay, so 2 different ways to solve the pH of a buffer, Henderson-Hasselbalch versus equilibrium. I'm telling you to always use Henderson-Hasselbalch, but you can decide that on your own, which one you like the most, okay? So let's go ahead and do a problem that utilizes this pretty little Henderson-Hasselbalch equation. I have a buffer, okay? I have given you the pH of the buffer solution. I have also given you the pKa of the buffer solution, and I want to know what's true about this buffer, okay? What I'm looking for is the relative concentrations of weak acid to conjugate base, okay? So you should be able, utilizing the Henderson-Hasselbalch equation, to determine who is in greater proportion, weak acid or conjugate base in this buffer solution. And I will draw the Henderson-Hasselbalch equation once more just to remind you what it looks like. This guy's on Socrative. Go ahead and get your answers in if you have yet to do so. Okay, so let's talk about this one. So the correct answer here was A, which I've listed as 1 up here, which is kind of confusing. But the concentration of weak acid is greater than the concentration of conjugate base. So how would I determine that? There are 2 things that I know about this solution, right? I know the pH of the solution, and I know the pKa of the acid. So if I go ahead and plug those values in, 4.82 plus log of A minus over HA, and I try to solve for this ratio. With this data, could I solve for this ratio? Yes, right? So to do that, I would subtract the pKa from both sides, right? Move 4.82 on the other side. That's going to give me a value of minus 0.57 is equal to log of A minus over HA. How do I get rid of the log? 10 raised to both sides. So 10 raised to this minus 0.57 gives me a value of 0.27 is equal to the concentration of A minus over HA. So who is greater here? If I take A minus and I divide it by HA and I get a fraction, who's got to be in a larger amount? HA. Okay, so that's how you would solve something like this. This essentially tells you that HA is greater than A minus. And again, sometimes I forget to put these concentration brackets, but just note that I'm talking about concentrations of these guys. Okay, so that's great. That's actually one thing that you would need to know if you actually wanted to make a buffer. So I don't think we go into that, but just as a note, knowing these ratios is important. All right, so now we're going to talk about how to calculate the change in pH upon addition of a strong acid or a strong base to our buffer solution. So I originally told you that buffers don't change pH, right? But that's not actually true. They do change pH, but according or like comparatively to something like water, how much of a change do you see in a buffer solution? Very little. Okay, so the whole idea behind a buffer is that they're going to resist changes in pH. They're still going to change pH, and we're going to be able to calculate that, but the change that you're going to see comparatively to if you just threw strong acid or threw strong base into water is going to be very, very, very small. Okay, so in doing these types of problems where we are calculating the pH of a buffer after addition of strong acid or strong base essentially occurs in 2 separate parts. Okay, so the first part is what we're going to call the stoichiometry calculation. What's going to happen is if we add strong acid, if we add strong base, it's going to change our relative amounts of weak acid and conjugate base. So we have to go in and we have to figure out using stoichiometry how much it does so. Once we have the new amounts of weak acid and conjugate base, then we're going to go in the second part of the problem and do the new equilibrium calculation to get pH of solution. Okay, and I'm going to demonstrate how we're going to do both of these parts in the next example. Okay, so let's make a buffer first off, and now we're going to change its pH. So the buffer that I'm going to utilize is this hydrofluoric acid buffer. Okay, so I have made a buffer that consists of 0.1 mole of hydrofluoric acid and has 0.1 mole of its conjugate base fluoride ion. Okay, so note we do have a volume for the solution. It is 1 liter. So we have this buffer. It's happy. It's by itself. And all of a sudden, we add 0.025 moles of strong acid. And again, what we're really adding here is this H+ ion. So how am I going to calculate the new pH of my buffer after the addition of this strong acid? So I'm going to start out by looking at the stoichiometry calculation. So what I'm going to do right now is I'm going to go ahead and write out my overall equilibrium problem before addition. Okay, we had our HF it's a weak acid, so we're going to write it out as this acid ionization reaction. We get our H3O plus and we get our F minus. And I'm just kind of doing this to show what we have before we do anything to this solution. Okay? Now I'm going to write out how many moles I have of both my weak acid as well as my conjugate base. So right now I have 0.1 of my weak acid, and I also have 0.1 of my conjugate base. So this is before anything has ever happened. All right, so now we come in and we disturb our little system by adding H+. And specifically, we add 0.025 moles of this H+. Now, how is this H+ addition going to affect this overall reaction? Who is it going to react with, the weak acid or the conjugate base? Right, so this H+, which we're adding, is going to react with our conjugate base, and who is it going to form in the process? Weak acid, right? So the H+ reacts with the conjugate base and forms more weak acid. Now, the whole purpose of this stoichiometry step is figuring out how this addition changes the relative amounts of these guys in moles, okay? So what I'm going to do now is I'm going to write a little BCA table, okay? So this BCA table is kind of like a little record-keeping log of how my moles are going to change in this overall process, okay? So B here stands for before, C stands for change, and then A stands for after. Please do not confuse this with an ice table. Okay, this has nothing to do with equilibrium. It's just trying to keep track of our various moles. All right, so beforehand, before anything has happened, I had 0.1 moles of fluoride, and I had 0.1 moles of HF. And I'm also going to put in this little before column how much H+ I have added to my buffer. Okay, so I'm going to go ahead and put in 0.025 moles of this guy. All right, so now these two are going to react, right? And I have two reagents here. I have H+, I have F-. Who's going to be my limiting reagent? Who are we going to completely run out of in this reaction? H+, right? We have a lot less of it. It is going to be our limiting reagent, right? So these guys are going to react. We're going to run out of it. So this is what's going to define our change. We're going to lose that amount of H+. We're going to lose that amount of F-. But now what's going to happen with HF? Stoichiometrically, how much HF are we going to gain? This 0.025. Okay, so this addition has changed my amount of conjugate base. It's changed my amount of weak acid. So afterwards, we no longer have any H+. It's completely reacted. We are only left with 0.075 moles of F-, and we are left with 0.125 moles of HF, weak acid. All right, so that's the stoichiometry step. What comes next? Because again, we want to determine the pH of this new solution that we have essentially created. So now we have our relative amount of weak acid and conjugate base. It's a buffer, still a buffer. We've got significant amounts of both of these guys. How would I go about calculating the pH of a buffer solution? Henderson-Hasselbalch, right? So now we have our new amounts in moles. We're going to take these guys and plug them into our Henderson-Hasselbalch equation, okay? So I'm going to go ahead and relist this because I get confused. H2O, H3O plus F-. And now I have 0.0125 moles of this, and I have 0.075 moles of this. Now, with respect to the Henderson-Hasselbalch equation, what do these need to be in? This weak acid and conjugate base. They're in moles right now, but when I draw out my Henderson-Hasselbalch equation, how do I list these? Concentrations. Okay, so this next little step, we're going to take these moles, we're going to convert them to concentrations before I plug them in to the Henderson-Hasselbalch equation. So if I have moles and I want concentration, what else do I need to know about this? the total volume of the solution, but that was nice and easy at the very beginning. It was just what? 1 liter, right? So I'll go ahead and divide my moles by my volume. So that's nice and easy because they just end up being numerically equivalent. Same thing over here. So now I'm ready to go ahead and calculate the pH of this new solution. What is the only other little piece of information that I need to know? Ka or pKa. So the Ka of HF is 3.5 times 10 to the minus fourth. And so then just taking the minus logarithm of that, I will get my pKa, which is 3.46. So now pH is equal to pKa, 3.46, plus log of conjugate base, 0.075, divided by weak acid. And we get a pH equal to 3.24. So easy, right? There is one little thing I want to highlight really quick. It's just kind of a simple step that I just want to note, okay? So when I plugged these concentrations in, right, if I had left them, let's just say, in moles per liter, so if I had taken this and plugged it in for my conjugate base over 1 liter, and I divided that by my concentration of HF, again, keeping those in moles per liter, what happens long-term to the volumes? They cancel, right? So do I actually have to include this step if the volume is the same? If we're in a buffer, they're going to have the exact same volume? No, I don't, because essentially they just cancel out. So I could have also just plugged in these numbers in moles, okay? I only tell you that because certain things you have to use concentrations for. This sometimes is not one of them, okay? So just note that if you always go back to concentration, you will never get the problem wrong. But if you're confident in the fact that you know what to do when plugging these guys in moles, then you should feel free to do that as well. Okay, so let's try one. I didn't need that slide because I did everything I needed to on the previous slide. So I have a buffer. It is an acetic acid acetate buffer. And to this buffer, I add strong base, sodium hydroxide. So I add 0.05 moles of strong base. I want to know what is the resultant pH of this buffer solution after the addition of the strong base, okay? The one thing it will help you with, if we're adding OH minus, who is OH minus going to react with? The weak acid or the conjugate base? Weak acid. It's going to make water, and what else? Because we have an OH and H, what's left over from the weak acid? More conjugate base. So in dealing with the stoichiometry, this is going to be the reaction that you're going to want to deal with. Okay, so as long as you guys are getting the first answer in, I'm okay with that. We'll go over the second one. Most people are struggling with that one. So we'll go ahead and talk about this one. All right, so I've written out what the reaction is that occurs. We've added strong base to our buffer. Before we ever added the base, how much weak acid did we have in moles? Because all of this, I should note that. Because with these problems, we just give you the moles. But if you don't have the moles, and you have the concentration and volume, before you do the stoichiometry problem, you always have to convert to moles, okay? Again, we don't have to worry about that because they already given to us in moles, but just note that when you're doing the homework and the exam, etc. Okay? So we have initially, before anything has happened, 0.350 moles of acetic acid, and then we also have 0.250 moles of acetate, our conjugate base. We are then going to disturb this by adding 0.050 moles of strong base, OH minus, hydroxide ion. Okay? Now, again, who is the limiting reagent in this problem where we have our two reactants going to make our products? Who's going to limit this overall reaction? The OH minus, right? We have much less of it, right? So when these guys react, we're going to completely run out of it. That's going to take away from our weak acid. And what is that going to do to the not concentration, but the amount of our conjugate base, our acetate ion? It's going to gain an equivalent amount, right? All right, so that is the change. Again, it's determined by who is the limiting reagent here, which is the hydroxide ion. So afterwards, we're going to completely consume all of the OH minus. We are going to be left with 0.300 moles of weak acid, and also 0.3 moles of conjugate base, okay? So now we have our values in terms of moles for our buffer. After this change, what am I going to do with these guys? If I'm ready to plug them in, because I want to know what the pH of this solution is, I have my amounts in moles. What do I need to do with them to determine the pH of this solution? I could plug them in directly, or I could go ahead and convert to concentration. So if I do that, I divide by the volume. It's going to give me 0.3 molar and 0.3 molar. So now to determine the pH, what do I need to do? Plug them in. I've got my conjugate base. This is my A minus. I've got my weak acid. This is my HA. What else do I need for this guy to determine the pH of this solution? I need the pKa. So I've got Ka up here. What is the pKa for acetic acid? 4.74. Minus log of that number is 4.74. So when I do this, pH is equal to 4.74. That ratio, 0.3 divided by 0.3, gives me 1, right? So what is log of 1? 0. So pH here is equal to the pKa of the acid because we have equal concentrations of weak acid and conjugate base. All right, so then as a little comparison, what would have been the pH if we had added this exact same amount of sodium hydroxide to water? 1 liter of water specifically. So sodium hydroxide is a strong base, right? We can assume that when we add it, it's going to completely dissociate into whatever cation there is in hydroxide ions, right? What I can do right now with this amount is I can calculate directly the concentration of OH minus that is present in this new solution, right? I have 0.05 moles. I have 1 liter total volume. So to do that, I'll just take those guys, 0.5 moles divided by 1 liter. This is going to give me an OH minus concentration equal to 0.05 molar. If I knew the concentration of OH minus, how could I get the pH from that? I could do something with POH, right? If I took the minus log of this OH minus solution. So the minus log of this guy is 1.3. How would I get the pH from the POH? So this would just be 14 minus 1.3, gives me a pH equal to 12.70. So same amount of sodium hydroxide. For water, before we actually added the OH minus, what would the pH have been if it was just pure water? 7, right? So for just a water solution, we essentially took a pH of 7 solution to a pH of 12 upon the addition of this guy. The pH of this buffer, before we actually added this OH minus, was something like 4.59. When we add the exact same amount of OH minus to this buffer solution, how does it change the pH comparatively? So if I had calculated the pH of this buffer before I had done anything to it, it would have been 4.59. When I added the same amount of sodium hydroxide, how did the pH change? Not very much, right? So in water, we took something that was 7 and jacked it up to about a 13 pH, whereas in this buffer, we had the exact same amount, exact same volume. We go from 4.59 to 4.74. So this is a nice illustration of the purpose of a buffer. It is to resist large changes in pH upon addition of strong acid and strong base. Okay, so we're going to use that. We're going to come back to this. This is going to be kind of central to our discussion of titrations. But before we get to that, there's a couple little loose ends I have to tie up with respect to the remainder of this chapter. Okay, so we have been dealing specifically with acid buffers, weak acid buffers. Okay, I also told you though that you can make a buffer via a basic buffer. Okay, so a basic buffer would have consisted of a significant amount of a weak base as well as its conjugate acid. So what type of weak bases have we been dealing with? Besides anions, we can ignore anions, just basic weak bases. What is our most basic weak base? So ammonia is our most basic weak, not basic, I guess I shouldn't say it like that, but it's the most plain weak base that we could possibly see, right? So ammonia is a weak base. We have seen it before. Why is ammonia a weak base? What does it have that's super central to being a base? This nice lone pair of electrons, right? So the conjugate acid of ammonia is going to be ammonia with an extra H added to it, right? So this guy is our conjugate acid of ammonia. What is this? NH4 plus, you guys should know that with your nomenclatures. Ammonium, right? So ammonium is one of our only cationic polyatomic ions, okay? So if we're gonna make a basic buffer, we're gonna have to get this guy into solution somehow. This tends to be a liquid, we don't have to worry about that. How do you think we're gonna get NH4 into solution? So probably, if this is going to be a cation, it's probably going to be paired with some sort of normal, negligible anion, right? So this is going to come in the form of some sort of salt, something like ammonium chloride, ammonium bromide, etc. That's going to be paired again with an anion that doesn't do anything to the pH of the solution. So if we're making a basic buffer, we're going to have a weak base, and usually the conjugate acid is going to get into solution in the exact same way our conjugate bases were, via some sort of very soluble salt. Okay? Okay, so with respect to basic buffers, we have defined the Henderson-Hasselbalch equation in terms of what? So it's pH is equal to what? Henderson-Hasselbalch, pH is equal to pKa. Okay, so with what we've been doing thus far, we've essentially defined the means by which we can determine the pH of a solution via the pKa of the weak acid, okay? This is a problem with respect to basic buffers because we don't usually have the Ka of the conjugate acid, right? Instead, what we are usually given is the Kb of the weak base. So this is fine. We can still use the Henderson-Hasselbalch equation to determine the pH of a basic buffer, but we're going to have to make one little change, right? If we are given the Kb of our weak base, can we determine the Ka of its conjugate acid? Yes. Okay, so the Ka of the conjugate acid would come from Ka times Kb equals Kw, and then we could take the minus log of that. There's also another little equation that would be very helpful at this point in time. and that's the fact, and I haven't derived this, I haven't talked about it, but pKa plus pKb equal 14, just like pH plus pOH is equal to 14. So you could determine the pKb, you could plug it in to this guy to determine the pKa and go about your buffer business as you would normally, okay? I usually don't ask questions about basic buffers, so just letting you know in case I forgot and I put one in the homework. So I just want to let you know that. Again, I wouldn't expect this on the actual exam. Okay, so a couple more things. Stick with me. We're almost done. We're going to skip this because, again, running out of time. Okay, buffers. Still talking about buffers. We're going to talk about buffers forever, okay? So next couple of things, we're going to talk about what makes an effective buffer, right? So a buffer has one job, and that is to not change pH significantly, okay? So we're going to talk about various properties or various characteristics of buffers that are going to allow it to do its job very effectively. So what's going to make an effective buffer? There are going to be two different things that we're going to define when we determine the effectiveness of a buffer. So the first one is its capacity, its buffering capacity. And the second one is going to be what's called its buffering range. Okay, so looking at the effectiveness of a buffer, we're going to talk about the amounts of weak acid and conjugate base that are going to make us an effective buffer. Okay, so two different things that we're going to look at is the relative amounts of our weak acid and conjugate base, as well as the absolute amounts of our weak acid and conjugate base. All right, so what makes a good buffer? What makes it very effective at doing its job? So first off, we're going to look at the relative amounts. So how much weak acid is there comparatively to conjugate base? So the most effective buffer, so it's going to be best at not changing pH when we add any type of acid and base, is going to come about when we have weak acid concentrations that are as close as possible to conjugate base concentrations. The closer these two are to one another, the better this is at buffering, okay, overall. So if I had two solutions where one of them had equal amounts of weak acid and conjugate base, and one of them had relatively very different amounts of weak acid and conjugate base, which one do you think would be the most effective solution? The first one, right? The one that has the closest amount, respectively to one another, of weak acid and conjugate base. Again, the closer these guys are, the better this thing is at buffering, all right? So this is what I mean about relative amounts. Now, what about absolute amounts, right? So if we have a buffer, and let's say this buffer has 0.5 moles of weak acid and conjugate base, and we compared that to a buffer that only had 0.05 moles, who do you think would be better at buffering? This is what I mean by absolute. Do you think the one with the most weak acid conjugate base, or do you think the one with the less weak acid conjugate base? So again, it's these guys that are actually going to be reacting with the strong H plus or the OH minus that's going to get added. So the more we have of them, the better this thing is going to be at doing its job, right? The more we actually add of our weak acid and conjugate base, the better it's going to be at actually buffering to a specific pH, okay? So again, for this guy, the more of the buffer that we put in, the better it's going to be at buffering. And then one more thing, talking about buffering effectiveness, we're going to talk about buffering range. So this idea of buffering range is kind of asking the question, at what pH values are buffers actually going to be effective at buffering? So the answer to that question is essentially kind of comes back to, again, these relative amounts of conjugate acid and weak base, okay? A buffer is going to be most effective when this ratio, this conjugate base over weak acid, is within an order of magnitude relative to one another, right? So this ratio needs to be less than 10, but it also needs to be greater than 0.1. If we're outside of this ratio, like if we're at a ratio of 100 or something like 0.01, then our buffer cannot actually buffer, okay? So what does this actually translate to with respect to pH? So if we plug these little ratios into the Henderson-Hasselbalch equation, what we find is that the pH at which we can buffer at is essentially either going to be -1 unit of the pKa or +1 unit of the pKa. Okay, so what does that mean exactly? So let's say that we have our acetic acid buffer. So this is going to be, he's going to abbreviate this guy as acetic acid acetate. The pKa of this buffer is 4.74. And what this thing tells us is that the range of pHs at which this buffer system is actually able to be a buffer is going to be within 1 unit plus or minus of its pKa. Okay, so that means that this can buffer at a pH from 3.74 all the way to 5.74. So plus or minus 1 unit of its pKa. If we have a pH that is outside of this range, acetic acid acetate is not going to be able to buffer outside of that range. Okay, so if you want to make a buffer, you need to know what pH you're going to be at. With that, you need to pick a buffer that has a pKa within plus or minus 1 unit of the pH that you're trying to buffer at. Okay, all right. One more thing, and then we'll do our last few questions. So this is our buffering range. Again, buffers are not able to buffer within plus or minus 1 unit of their pKa or outside of that range. The last little thing that we're going to define is something called buffer capacity, okay? And this kind of comes back to the absolute amount of buffer that we're putting into a situation, okay? So let's imagine that we go back to this hydrofluoric acid fluoride buffer. Let's imagine that we have this great buffer. It's got really close values with respect to one another. So it's happy, it's buffering, it's happy, it's good, okay? Let's then say that we add about 0.1 moles of strong base. So we had a buffer, we had weak acid, we had conjugate base, and to that buffer we have added 0.1 mole of OH minus. What's that going to do to our buffer? So OH minus, who's that going to react with? The HF or the F minus? So this guy would react with the HF, and it would make more F minus in the process as well as water, which is not necessarily what we care about. If I had only 0.1 moles of my weak acid and I add 0.1 moles of strong base and they react completely, do I have any more weak acid? No, right? So if I add enough strong base that I completely use up all of my weak acid, do I have a buffer any longer? What do we have to have a buffer? You have to have significant amounts of what? A weak base and a strong acid, okay? If we add something that completely depletes all of our weak acid, do we have a buffer anymore? No, okay? So this is what I mean by buffer capacity. How much strong base or strong acid can we add before we destroy our buffer, right? Before we completely run out of one of the components that makes it a buffer. Again, the more stuff you have, the more acid and base you're going to be able to neutralize before that actually occurs. Okay, so those are my loose ends. Let's do 2 questions, and then we'll finish up for the night. So this one is going to take into account what I've essentially just talked about. I'm going to be looking at buffering range as well as buffering capacity. These should not be calculation-based necessarily. Okay, so for this one, I want to make a solution that is buffered at a pH of 4.25, and I am trying to pick the best acid system to utilize to make this buffer. Okay, so this is taking into account this idea behind buffering range. So the best, I guess I want the closest. That's what I would say. Best buffer. Okay, so most of you guys have gotten this in, about 75% got it correct. So the correct answer here is formic acid. And again, with respect to these pKa's that I've given you, these are going to tell you at the pH range, essentially, that these various acid systems are capable of buffering, right? So for chlorous acid, what pH range would this be capable of buffering around? So it's going to be plus or minus 1 unit of the pKa. So this would be 0.95 to what? 2.95, right? Second, nitrous acid, this would be 2.34 all the way to 4.34, which is in our pH, right? This is the pH that we wanted. For formic, this is 2.74 to 4.74, and then hypochlorous would have been 6.54 all the way to 8.54. So plus or minus 1 unit of the pKa. Now then, with that, there are two possibilities. There's nitrous and there's formic. What we want is the one with the pKa that is actually closest to the pH at which we are trying to buffer around. Okay? So because of that, 7 or 3.74 is closer than 3.34, and so the formic acid would be the best buffer here. Okay, so one more. So I have a buffer system. I've got 1 liter of 0.1 molar hydrofluoric and 0.05 molar sodium fluoride, and I want to know which of these actions completely destroys my buffer. Overcomes the buffering capacity. Okay, so most of you guys have gotten your answers in. This is a little bit worse of a correct answer, so we have 50% getting this correct. So the correct answer here is A, it's HCl addition. So it's really important to note when we're looking at these buffering capacities and we're looking at how these things are going to change the relative amounts, this always has to be in moles, right? So this problem right now is giving us a volume and a concentration. So it would be important to go ahead and convert these to moles first. It's a nice little easy conversion though because the volume is 1 liter. So before we do anything, we have 0.1 moles of HF and we have 0.05 moles of F minus, okay? All right, so a lot of people went with the addition of sodium hydroxide. So sodium hydroxide, we're adding 0.05 moles of it. Which one is it going to react with, the HF or the F minus? Right, so this guy is going to react with our HF. So we'd have OH minus plus HF making water and F minus. If we had 0.1 of these and we're adding 0.05 of these, does this addition completely get rid of all of our HF? No. So we still have some conjugate base, and we still have some weak acid, and we still have conjugate base, and we still have a buffer. This one, on the other hand, 0.05 moles of H+, that's going to react with our conjugate base. And since there are equal amounts of those, it's going to essentially destroy it, right? It's going to take away all of our conjugate base. So then we'd only be left with weak acid. Is weak acid by itself a buffer? No. Okay, so this one would not destroy. This one would. What about this one? What would this make it? So if we added a bunch of sodium fluoride, what would that do? So all that would do is add more of this guy. If we added 0.05 of it, then we would have 0.1. So what would it do long term? Now we have very similar concentrations of weak acid and conjugate base. Makes it a better buffer, right? So B here would just essentially make it much better at actually buffering because we'd be getting these values equal to one another. And that's when a buffer is best. Okay, so that's all I have to say. I will see you in the lab. Okay, so in the second part of this chapter, we're going to deal a lot with titrations. So we've talked about titrations before. The way that we have utilized titrations in the past and things like 151 is we have had, let's say, some sort of unknown concentration. So let's say that we had a base, something like sodium hydroxide, and we didn't know what its molarity was, what its concentration was, but we had an acid, let's say this was something like HCl, and we did know its concentration. So this was our known value. So in acid-base titrations before, we would be able to utilize our known concentration to determine the unknown concentration of whatever we were looking for, right? And so what that really heavily relied on was our use of what is called a pH indicator, right? So at a pH indicator, what that thing would do is it would turn our solution a color when we reached the equivalence point. So at the equivalence point, the number of moles of acid were equal to the number of moles of base. We are able to utilize all of that information, again, to go back and determine the concentration of the unknown. Okay, so that, again, is how we have utilized acid-base titrations in the past. We've used an indicator, and it's only been to look at concentrations of things and not necessarily the pH of things. So now, in this chapter, we're going to take titrations a little bit further, and we're going to be essentially monitoring the pH throughout the entire course of a titration. And what we're going to be able to generate from that is something called a pH curve or a titration curve. So another word for these pH curves is titration curves. Okay, so what do those actually look like? Okay, so we're going to spend some time with these with respect to these pH curves and these titration curves. And most importantly, we're going to go over two different types of titrations. We're going to talk about first, which is what I'm going to talk about today, the titration curve that is going to be generated when you titrate a strong acid with a strong base. And then in class, we're going to go over kind of the more important type of titration curve, which is the titration curve for a weak acid being titrated with a strong base. Okay, so again, what do these guys look like? So we're going to start with a strong acid and a strong base. And so to highlight what titration curves will look like, over to the right here, I have the titration curve for a strong acid, strong base titration. So the strong acid was HCl, and the strong base that we used was sodium hydroxide, okay? Okay, so experimentally, what type of setup would we have that would actually generate stuff like this? So if you want to imagine what's happening in these overall titrations, for this type of titration, you would have your strong acid, so this is going to be HCl, in, let's say, an Erlenmeyer flask or some sort of beaker or something. You would have your burette as usual, and the sodium hydroxide, the strong base, would be coming from your burette, and you'd be measuring volumes of sodium hydroxide released. Instead of having an indicator, right, instead we're going to have a pH electrode and a pH meter, right? And so we're going to be measuring essentially the pH as we add volumes of sodium hydroxide from the burette, right? So our plot here is pH as a function of the volume of sodium hydroxide added, or just the amount of sodium hydroxide added, okay? So there's going to be a couple of different points in this curve that are going to be important. So number one is the first point right here. So this is something that we'll call the initial pH, okay? So initial pH, or initial point in this titration curve, is essentially just going to be the pH of the HCl before we've actually added any type of NaOH, okay? Another important point is the equivalence point. And so for these titration curves, the equivalence point manifests itself as this sharp inflection in this sigmoidal curve, right? So we start at very low pHs because we have a very acidic solution. The pH is going to just kind of slightly increase as we continuously add NaOH until we reach the equivalence point, and we'll see this sharp rise in pH at the equivalence point. And then after the equivalence point, we get the second or third region, which we will just kind of categorize as after the equivalence point. Okay, and so we're going to calculate the pHs of this solution, of this titration, at these various different points along this curve. Okay, so where do we usually start with respect to these titrations? So what I always tell everyone is always start by calculating the equivalence point in the titration, okay? So as a reminder, what the equivalence point was and what we've known as the equivalence point up until this point in time, the equivalence point was the period in time, or the point in time in a titration where the number of moles of acid equal the number of moles of base. Okay, so that's not going to change. It's still going to be the exact same definition. Number of moles of acid equal number of moles of base, except what we're going to be calculating now for this equivalence point is not necessarily moles or concentration or anything like that. Instead, we're going to be determining the volume of base required to get to this point. Okay, so for these titrations, the equivalence point kind of takes on a new definition, and we're going to look at it as the volume of base required to reach the equivalence point. Okay, and so for all of these titration curves, I always suggest that you start at this point in time by taking whatever information you have and calculating the volume of base required to reach the equivalence point, which is what we essentially determined to be the equivalence point, okay? So let's say that we have a titration. So we've got HCl. We've got HCl in our little flask, and we know, it's a really ugly flask, we know the volume of this HCl solution. So there's 25 milliliters of HCl in this flask, and it has a concentration of 0.1 molar. Okay, so again, this is our strong acid. To that, we are adding our strong base. So this is sodium hydroxide. We're going to be adding volumes of the sodium hydroxide from our burette. And this guy, our strong base, has a concentration of 0.1 molar as well. Okay, so now the first part, what we're going to do is calculate the volume required to reach the equivalence point. Okay, so again, we're going to utilize our definition, or our working definition of what an equivalence point is. Number of moles of acid equals number of moles of base. So to utilize that, we're going to take what we know, our volume and our molarity of the acid, and we're going to calculate how many moles of acid are actually in here to begin with. Okay, so again, molarity is defined as the moles of solute divided by volume in liters of solution. So we know the molarity of our HCl. This is 0.1 molar. That's going to be equal to the number of moles of HCl that are in there, divided by the total volume, and that total volume needs to be in liters, right? So for this HCl solution, we have 25 mils. Converted to liters, that is 0.025 liters, okay? So this is for our HCl, or the acid. So I'm going to solve for X. X ends up being 0.0025 moles, and that's going to be of our HCl. So that's how much HCl was initially in our little flask. Now we're going to utilize that information to determine how much NaOH we need to add to essentially give that exact same number of moles of NaOH, right? So again, at the equivalence point, 0.0025 moles of acid is going to equal the same number of moles of NaOH, of our base. So it's going to be equal to 0.025 moles of NaOH. So now we know how many moles we need to supply of our sodium hydroxide from the burette. To calculate the volume, we're also going to take this. We're going to take our number of moles as well as the molarity of the sodium hydroxide to calculate what volume is required to reach that point in time. Okay, so for sodium hydroxide, we know that our concentration is 0.1 molar. Again, the question that we're asking is what volume are we going to need to give us this same number of moles, this 0.0025 moles of NaOH. 0.0025 moles of NaOH. And so we solve for X. X ends up being 0.025 liters, which converted to milliliters is 25 milliliters. Okay, so again, we've got 25 mils of our HCl in the flask, and we're saying how much of this NaOH is going to get us to the equivalence point. That's essentially what we have just solved for. Okay, so 25 mils of NaOH is what is required to reach the equivalence point in this titration. Okay, so that's usually step one. Now, step number two, after you've calculated that equivalence point for the titration, you're now going to go in and start to calculate the pH at various volumes of sodium hydroxide added, okay? Okay, so the first one that you're usually going to calculate is just going to be the initial pH. And so the initial pH is the pH whereupon we have only added 0 NaOH, right? So it's just the initial pH of the HCl solution. So again, for our little HCl solution, we know HCl is a strong acid. So it completely ionizes to form H3O plus Cl minus. In this initial solution, right, just HCl, we haven't added any sodium hydroxide from the burette. It had a concentration of 0.1 molar. If I want to calculate the pH of the solution, I need to know the hydronium ion concentration, right? The number of protons, the number of H3O plus. Since this is a strong acid, I can assume that all of it goes to form products. So my concentration of H3O plus is also 0.1. My concentration of Cl minus is also 0.1, but that doesn't necessarily matter, right? So now to calculate the pH of this, all I need to do is take the minus log of my concentration of H3O plus, which is the same exact thing as just the concentration of initial acid. And that gives me a pH here equal to 1. Okay, so first point in this titration, calculating the initial pH before we've added any NaOH is just going to essentially be calculating the pH of this acid solution, right? You just take the minus log of the concentration of strong acid, and that is your first pH. Okay, so now after we have calculated the initial pH, we're going to move on and we're going to start calculating the pH after we start to add sodium hydroxide from the burette, okay? All right, so again, to kind of illustrate the situation, we've got our flask. It has a certain number of moles, right? So we know that the HCl had a volume of 25 milliliters. It had a concentration of 0.1 molar, okay? And then we've also already calculated the number of moles. So we did that when we calculated the equivalence point. This ended up being 0.0025 moles of our H3O plus, our HCl, okay? All right, so again, this is that initially. Now what we're going to start doing is we're going to start adding NaOH from the burette, okay? So let's say that we start by adding only 5 milliliters. So we add 5 mils of our 0.100 molar sodium hydroxide. So now to calculate the pH of this resulting solution, so we're going to add 5 mils to our flask, and again we're going to measure or calculate the pH. We need to consider what type of reaction is actually going to be taking place between the sodium hydroxide and the HCl, all right? So in this reaction, for every one hydroxide molecule or mole that we add, we're going to react with an H3O plus to form water. Okay, so this is kind of like what we're doing right now is looking at the overall stoichiometry with respect to what we had and what is left over after we've added this amount of sodium hydroxide. So we're kind of questioning right now what we had, what we've added, and then what's left over to get the new pH for the solution. So to move into this type of stoichiometry-based problem, we first need to calculate how many moles of sodium hydroxide have we added when we have added 5 milliliters of this 0.1 molar solution. Okay, so to do that, we'll go back to the molarity. So molarity of this sodium hydroxide solution was 0.1 molar. We're going to calculate the number of moles of hydroxide, that we have added when we have added 5 mils. And again, when we take our 5 milliliters, we're going to convert it to liters. So that is 0.005 liters. All right, so now if we take the concentration, we multiply it by the volume, we're going to get the number of moles of sodium hydroxide added. That ends up being 0.0005 moles of OH minus. Okay, so we had this much, H3O plus. We've now added this much of OH minus. So what we're going to do is we're going to make this little table, and we're going to call this a BCA table, before, change, after, to kind of keep track of what we had, what we have left, and then calculate the pH from that. Okay, so we're going to take our little reaction up here, our little stoichiometric reaction, where we have our OH minus reacting with our H3O plus going to form water. And we're going to write over to the side BCA. So please do not confuse this with an ice table. All this is like kind of like a record-keeping type table, right? We're going to say what we had, what we've added, how it's changed, and what we have after. So B here stands for before C stands for change, and then A stands for after. And again, this is not an ice-based thing, so we're not going to be using any type of X's or anything like that. All right, so before, with respect to H3O+, that is the initial amount of moles of H3O+ that we had. So we've already calculated that. So that was 0.0025 moles of H3O+. And what we're also going to write in for before is the amount of OH- that we have added. So we have now added, when we added the 5 milliliters, 0.0005 moles of OH-. Okay? So now we're going to look at this, right? We're going to say, okay, we had this much. We have added this much. Which one is the limiting reagent, right? When these guys react, which they're going to, one of them we are going to run out of first, okay? And so that one, or that limiting reagent for this problem, is the OH-. There's much less of it comparatively to the H3O+. And so the limiting reagent is going to define the change here, right? So for every one of these, we're going to utilize one of these, and we're going to make 2 of these. For this type of problem, we don't care about water because it's not going to do anything, right? We're just essentially keeping track of H3O+ OH- using this table. All right, so because of that, our OH-, because there's less of it, we're going to use it all up entirely in the reaction. So we're going to lose that much of that guy. We're also going to lose the equivalent amount of our H3O+. So after this reaction has occurred, we have 0 of the OH-, but now we have 0.0020 moles of our H3O+. Okay, so again, how many moles do we initially have of H3O+? How many moles of OH- have we added? And then what's left over when they fully react? All right, so we are left with H3O+. So now if we want to calculate the pH of this new resultant solution, we're going to take the moles that we have left over after this reaction, and we are going to calculate the pH utilizing that, right? So there were 0.0020 moles of H3O+ left over. To calculate the pH, we need the concentration of H3O+, right? Right now, all we have is the number of moles. So now to calculate the concentration, we need to take one little piece of information back into play here, and that's going to be the volume, right? So molarity, again, is moles per liter. So to get our new concentration of H3O+, we're going to take the number of moles that are left, and we're going to divide it by the volume of the solution. So now it's important to note this is the volume of the new solution. So new solution. So that's going to be the addition of the volume that we originally had, right? So there was originally 0.25 or 0.025 liters, but now how much have we added? We just added 5 milliliters of volume, right? So we're going to have to add that in when we calculate this new volume, and then when we calculate the concentration overall. So this guy on bottom is going to be the initial volume plus whatever we have added, which for this problem was 5 milliliters or 0.005 liters. So when we do that, we're going to get a new H3O+ concentration of 0.0667 molar. Once we have our concentration of that, to calculate the pH, all we need to do is take the minus log of that. So minus log of 0.0667 gives us a pH equal to 1.18. Okay, so lots of little bits and pieces at play here. We had initially HCl. We have now added a volume of sodium hydroxide to our flask, right? We had to calculate, using the stoichiometry of the reaction, how many moles of H3O+ we had left. So that's what I did on the last page. And then to get the new pH, we're going to take those moles, and now we had to redivide it by our new total volume to get the new concentration, and then take the minus logarithm of that to get the pH. All right, so we can continue to do that as we move further and further into this titration, right? So we just calculated the pH after adding 5 mils of sodium hydroxide. We could do the same thing after adding 10, or 15, or 20 mils of sodium hydroxide. We can use the exact same method by which we utilize for 5 mils, right? So let's say that we've moved on in this titration, and now we have added 15 mils of sodium hydroxide. How do I calculate what the pH is after this 15 mil addition? So we follow the exact same format. The first step in this would be determining the number of moles of NaOH added when we have added this 15 milliliters. So to calculate that, we would take the concentration of our sodium hydroxide solution and we would multiply it by the volume that we have now added to solve for the number of moles. So 15 milliliters converted to liters is 0.015 liters. When we solve for X, which again is the number of moles of hydroxide ion that we have added, this ends up being 0.0015 moles of OH minus. So we would then take that and we would go back to our little reaction, our reaction stoichiometry. So OH minus plus H3O plus goes to make water. We would write the beforehand number of moles, right? So again, for H3O plus, that came from the original calculation. Originally, there were 0.0025 moles of H3O plus in our little flask. We have now added 0.0015 moles of sodium hydroxide when we have added 15 mils. And so again, the change is going to be determined by who is the limiting reagent, right? Who are we going to run out of in this reaction? For this one, it again is the sodium hydroxide. This 0.0015 is less than the 0.0025. So we're going to completely run out of that one. So that's going to give us a number of moles of hydroxide ion as 0 afterwards. And we're going to subtract the exact same number of H3O pluses away from the before amount, right? So that's going to leave us with 0.001 mole of H3O plus. And again, we don't care about water at this point in time. So that's how many H3O pluses we have left. To calculate the pH, we then need to take that and calculate the concentration of H3O plus in our new solution, right? So we know how many moles we have. Now we just need to divide that by the total volume of the solution. So again, this was the 25 milliliters that was present originally, plus the addition that we have made. So this is now 15 mils. So 25 plus 15, so 25 plus 15 mils gives us 40 milliliters. And when this is converted to liters, this is 0.040 liters. So our number of moles of H3O plus divided by the volume, the new volume, gives us a concentration equal to 0.025 molar. And so then for the pH of this, we just need to take the minus logarithm of our concentration, which gives us a pH equal to 1.60. So again, multiple steps involved here. Number one, we need to calculate the moles of strong base that we have added, given whatever volume and whatever concentration we have added. We need to then utilize that to calculate the number of moles of H3O plus left. With that, we're going to calculate the new concentration of H3O plus by including the total volume. And then once we know that, we're just going to take the minus logarithm of it to give us the pH overall. Okay, so we can continuously do that, right? So we calculated the pH of this titration at 5 mils. We calculated it at 15 mils, right? But for any point in time between the initial pH, which is what we calculated, and the equivalence point, which is something that we've also already calculated. So just as a reminder, for this titration, the equivalence point was going to be at 25 milliliters. So at any addition between the initial pH and the equivalence point, we're going to calculate the pH in the exact same manner. We're going to figure out how much OH minus we have added, how much H3O plus is left over, and then what is the new concentration of the H3O plus, and then the pH from that. Okay, so for example, I give you the pHs for 10, 15, 20 here, but I could also ask you about the pH of this titration at 17.5 milliliters of NaOH added. Okay, so again, you go about answering that question in the exact same format that we did for 5, 15, so on. All right, so then after that, we hit the equivalence point, right? And so at the equivalence point, which is 25 milliliters, which is something that we've already calculated. So at this point, the number of moles of OH minus that we have added are now numerically equivalent to the number of moles of H3O plus that were there to begin with, okay? So we go back to our little equation. We had OH minus plus H3O plus, right? They go to make our little water. They neutralize each other. And so at this point in time, at the equivalence point, the number of moles that we have for OH minus is equal to the number of moles that we had for H3O plus. So they have completely canceled each other out, right? Both of them are gone entirely. They have both neutralized each other. And so the only thing that we have left in solution at this point in time that is going to affect the pH of the solution is just water, all right? So all is just going to be, again, just water. Right, and so we know what the pH of water is, right? Because for water, we have equal concentrations of H3O plus, OH minus. Both of those have concentrations that are equal to 1 times 10 to the minus 7th. So the pH of water and the pH at the equivalence point in this titration is just 7. It's just neutral, all right? So for any type of strong acid, strong base titration, the pH at the equivalence point is always equal to 7. Again, because at the equivalence point, the only thing that's left in solution is water, and water has a pH of 7 due to its autoionization. So we can go ahead and plot that on our titration curve now at pH equal to 7 at our equivalence point, right? So now we've started to form this sigmoidal shape to our curve. All right, so now we've reached the equivalence point. That's great. What happens as we move past the equivalence point? So let's say that we move past the equivalence point. The equivalence point was 25 milliliters, but now we're going to continue on in this titration, and we're going to move on to a volume of sodium hydroxide added of 30 milliliters. How are we now going to calculate the pH of this solution? All right, so it's going to be the exact same initial starting point that we've done for all of these other volumes, right? I'm going to take my volume of sodium hydroxide. So I've got sodium hydroxide. I've added 30 mils at this point in time. I'm going to take my volume and I'm going to multiply it by the concentration to solve for the number of moles of OH minus that I've added. All right, so 30 milliliters converted to liters is 0.030 liters. And so after adding 30 mils of sodium hydroxide, I have added 0.003 moles of OH minus. Okay, so same exact thing that we have just done. You figure out the number of moles of strong base that you've added to this titration. Now we're going to go back to our little stoichiometry table. We're going to write our reaction. H3O plus goes to make 2 waters. And we're going to go ahead and fill in our before, right? So when we add these two things together, we have added 0.003 moles of OH minus, and we initially had 0.0025 moles of H3O plus that were in the flask at the beginning of the titration, right? And so now, after we've moved past the equivalence point, something has changed. Now, the H3O plus is our limiting reagent, and the OH minus is our reagent in excess, okay? So because of that, the change is not going to be defined now by the OH minus, but instead by the H3O plus. We're going to completely run out of H3O plus, and we're going to have an excess amount of OH minus left in the flask afterwards, right? So when we calculate this, we find that we have 0.005 moles of OH minus, nothing here in this guy, okay? So now the OH minus, the excess amount left in the flask after we have passed the equivalence point, is what is going to be determining the pH of our solution moving forward. So now what are we going to do with this excess OH minus? So we're going to take those number of moles that we had. So we had OH minus after our H0 plus and OH minus had completely reacted. We were left with 0.0005 moles of OH minus, and we're again going to calculate now the concentration of OH minus, right? We'd been calculating the concentration of H3O plus before. Now that's going to change, and we're going to calculate the concentration of OH minus. So this is going to be the number of moles of OH minus divided by the total volume of the solution. And so total volume here is going to be again the volume that we initially had in our flask before we started the titration, and now we're going to add to it the volume that we have added from the burette. Right? So total volume is 55 milliliters, which is equal to 0.055 liters. So we're going to take that and we're going to divide our number of moles by that total volume. And that's going to give us a concentration. Of course, I didn't do this. So 0.0005 divided by 0.055 gives us a concentration of 0.0091 molar. Okay, and this is OH minus concentration. All right, so now we still want the pH. We're still measuring the pH of the solution. We have the concentration of OH minus, and we know some relationships between OH minus and H3O plus, and then therefore pH as well, right? So right now, what I'm going to determine is the pOH, right? I'm just going to take the minus logarithm of my OH minus concentration. That's going to give me a value equal to 2.04. And then I also know that pH is equal to 14 minus pOH. So I'm going to utilize that relationship to calculate pH. So 14 minus 2.04 gives me a pH here equal to 11.96. So then we can go to our little 30 mils of sodium hydroxide and plot our 11.96 pH. Looks like it's like above that. Anyway, okay, so that is how you would go about calculating the pH after we have passed the equivalence point. So now we have OH minus as the excess reagent. It's going to be dominating the pH of the solution, and so to calculate the pH, you have to take in its concentration or calculate its concentration, calculate the pOH, and then get the pH from that. And so you can continue to do that for however many milliliters past the equivalence point you want to go, right, to get this nice, beautiful little S-shaped sigmoidal curve. Okay, so that is the overall titration, right? We started initial pH before we had added any sodium hydroxide. We calculated the pH in between the initial and the equivalence point, and then I also showed you how to calculate the pH after you had passed the equivalence point. And so overall, for these types of strong base, strong acid titrations, right? So we have our acid in the flask initially. We are titrating it with the strong base. There are, again, going to be certain little regions that you guys should be familiar with calculating the pH for. The first region was the initial pH before we added any sodium hydroxide. The second region is in between the initial pH and the equivalence point. So this is when we have H3O plus in excess. The third region is the equivalence point, and you shouldn't have to do anything for that besides know its value, know what volume you need to add of sodium hydroxide to get there, but the pH of the equivalence point is always 0 for this strong acid, strong base titration. And then after the equivalence point, that is the fourth region, we have OH minus in excess. So again, I demonstrated how you would calculate the pH for that region of the curve. Okay, so this is a nice little summary slide that kind of just writes out in words what I just stated on the previous slide. So feel free to look at this on your own. And then in this last little bit, we have another titration, all right, practice. And so I would suggest that you maybe go over these problems. They will probably likely be on the quiz, all right? So in this titration, in this practice titration, I give you a solution of hydrobromic acid. It has a concentration and a volume, and you're going to be titrating it with a solution of potassium hydroxide. So again, if we draw out what this would experimentally look like, the HBr is going to be in our flask. It has a concentration of 0.175 molar and a volume of 35 milliliters. So this is our initial solution. We are going to be titrating it with potassium hydroxide, given volumes of potassium hydroxide that has a concentration of 0.2 molar. Okay, so for the quiz, I will go ahead and tell you exactly what you will need to know. I will probably have you calculate the initial pH of this titration. I will probably have you calculate the volume of the potassium hydroxide that's required to reach the equivalence point. I will have you calculate this guy. And just as a give me, because I've said this already, you should be able to know this immediately, I'll probably have you tell me what the pH of the equivalence point would be for this titration, given that it is a strong acid with a strong base. Okay? All right, so in this last little slide, we have been titrating a strong acid with a strong base, right? So the acid has been in our flask, the base has been in our burette, and we have been adding base to acid in this overall titration that we've been talking about. We can also do the reverse, right? We could have a strong base and we could titrate it with a strong acid. So what do I mean by that? So let's imagine that in the reverse, we've got our flask and it has our base. So let's say this is something like sodium hydroxide, and to it we are adding a strong acid. Let's say this is something like HCl. Okay, we can also calculate the pH at various stages along this titration curve, right? It's only going to be different with a couple different respects to what we were doing before, right? So for example, if we had this strong base, strong acid titration, and we initially measured the pH, then the initial pH would be very basic, right? Because we would have not added any HCl at first. And so in the titration for this, we would start initially at a very basic solution, right? Again, the equivalence point, regardless, would still be 7 because it's strong base, strong acid. At the equivalence point, there's only water left around to influence the pH of the solution. The pH of water is 7. And so still, the equivalence point would have a pH equals 7. But in going between the initial pH and the equivalence point for this strong base, strong acid titration, the initial parts here have OH minus in excess, right? So you would have to go about calculating how much OH minus is in excess at each given volume along this part of the curve. You would have to calculate the pOH from that, and then you would get the pH from that. Equivalence point again is the same, but then once we move past the equivalence point and these type of titrations, we have H3O plus in excess, right? So it's, again, with this strong base, strong acid titration, the titration curve is similar. It's just kind of like the inverse of what we saw before. So we start basic, we go towards more acidic, and then once we move past the equivalence point, we are now in this acidic region. I usually don't ask a strong base, strong acid type question, right? So this is just letting you know, hey, this is what the curve would look like. I'm probably not going to ask any type of questions related to this. And then finally, if you guys wanted more practice, there is a question. This is going to be a strong base, strong acid titration, right, where we have the strong base. We're going to start very basic. Initially, we're going to be adding acid, strong acid to that strong base. So again, we would get a nice titration curve like this, the inverse of what we saw for the strong acid, strong base. If you want to go ahead and practice with some of these problems, feel free, but I am not going to go over those in this presentation. And so I think that is it for now. So again, this entire video was going over the titration curve and how you could calculate the pH at various regions along the titration curve of a strong acid being titrated with a strong base. I have given you indication of what questions I'm going to ask on the quiz, so make sure to go back and be capable of calculating those before you start the quiz.